Welcome to a new lecture of mechanics in which we will learn how to calculate the elongation of axially loaded bars, such as the bars that we typically have in a truss. Now, let's see how we can derive the formula for the elongation delta L of a short straight bar, which is, as I said, loaded axially. We will begin from the Hooke's law, including the constant of proportionality, and that is the Young's modulus, in which we've determined that the stress equals to E times epsilon, the modulus of elasticity, times the strain. Now we can express the stress as the force divided by the cross-sectional area and the strain as the elongation divided by the original length. And from here we can calculate the elongation delta L as equal to PL over EA. Of course, in this formula, delta L is the elongation, and this is typically calculated and expressed in millimeters. P is the axial force acting on the member in newtons. L is the original unstretched length of the bar, also given in millimeters, not in meters, in millimeters. And then at the denominator, E is the modulus of elasticity, which is the property of the material, given in megapascals, or it's the same thing in newtons per millimeters squared. And finally, A is the cross-sectional area of the bar, which is also given in millimeters square. Now, a word of caution here: please ensure that your units are always consistent. So if you use the units that I noted above, then that's perfectly fine, because otherwise the result will be totally incorrect. So please pay attention to the consistency of units. Delta L equals to PL over EA, a very important formula that you should remember. And this will help us determine the elongation of straight bars loaded axially. Now I'd like to tell you a few words about a sign convention related to the elongation of straight bars. So let's assume first a bar like this, which is subjected to a force P, which makes the force, or has as a result, the bar becoming longer by an elongation delta L. So in this case, we say that the axial force is a tension force, and due to this tension force, the bar will become longer, and hence we term this as being positive. Now, if the same bar is subjected to the same force but having opposite direction, then the bar, the short bar, straight bar, will shorten up this time, also by an amount, say delta L. Now in this term, the force is a compression force, and as a result, as I said, the bar will become shorter. So for tension forces, the bar becomes longer. For compression forces, the bar becomes shorter. Now, by convention, we assume that tension is always positive and compression is negative. So this is about forces. And the same sign convention applies to the elongation as well. Which means that the elongation when the bar becomes longer is a positive elongation, and the elongation when the bar becomes shorter is negative. Now, a small note, the term elongation is used for both when the bar becomes longer or when it becomes shorter. It may sound a little counterintuitive for the latter case, but we always call this deformation elongation. It's just that in certain cases the elongation is positive when the member becomes longer, and in other cases the elongation is negative, of course, when the member is under compression and it becomes shorter because of that. So, this is about it with regard to determining the elongation of a short straight bar loaded axially. And I would like to thank you very much for watching this lecture, and I will see you, of course, at the next one.